Hello, this is Dr. Strickland. In this video, we will finish up talking about the reactions of carbonyl compounds with carbon nucleophiles. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the things we will do together in class. So we were talking about the reactions of aldehydes and ketones with Grignard reagents, but it turns out that a lot of compounds will react with Grignard reagents. For example, acyl halides and esters are very reactive towards Grignards. And in fact, they will add two equivalents of a Grignard reagent because the ketone intermediate is also very reactive towards Grignard reagents. So the first thing I want you to do is to take a look at these two general reaction patterns. You'll see that in both cases, you're making a tertiary alcohol and that two of these have ended up in the product in both cases. What that means is that you can use this reaction to make a tertiary alcohol as long as it's okay if two of the alkyl groups attached to that middle carbon are the same. So take a look at these two sample problems. I want you to draw the products of both of these reactions and then come on back. All right, welcome back. Let's see what they look like. Now, this is the carbon that's kind of the star of the show. So I think a lot of times it's a good idea to feature that carbon in the product. So in this case, we've got an alkyl portion that's got a branch here, couple of methylene groups, and then the carbon that's the star of the show. So you might just draw out these bonds so that you can remind yourself of what gets attached to it. Now it's the alkyl portion of the Grignard reagent that adds twice. So this product looks like that. And if you're working in skeletal structure, it's much the same. This is the carbon that's the star of the show. So we'll put the hydroxyl group of the alcohol there. And then we've got a couple of ethyl groups. So I think I'm going to draw them like this. Okay, let's take a look at what the mechanism looks like. I'm going to do it with the ester. It would look very much the same if you did it with the acyl chloride. But in the first step, the carbonyl compound, in this case, both of them are carboxylic acid derivatives, is attacked by the alkyl portion of the Grignard. Because remember that that bond that joins the carbon to the metal is a very polarized bond. So much so that it's like the carbon that's attached to the magnesium has a partial negative charge. For that reason, it can use those electrons to make a new covalent bond like that. And that gives us a tetrahedral intermediate. And we saw lots of tetrahedral intermediates when we were doing our reactions in the last chapter. And the thing about carboxylic acid derivatives is very often they can eject a weakly basic portion. Now, since we don't have any acid here in here at the moment, there's no reason why we can't kick out a negatively charged piece. You can only kick out a negatively charged piece if you've already got a basic situation. So that brings us to here. And I'm just going to bring that alkyl group around. Okay. Attacked by Grignard number 2. In very much the same way. So that gives us a second tetrahedral intermediate. Like this. But now there is no weakly basic piece that can be ejected. That's why it will just sit there and look at you until you add some aqueous acid. And at that point, you can protonate that negatively charged oxygen. Now, sometimes when you have aqueous acid in that second step, it will show as hydronium ions. Sometimes it will show as water and hydrochloric acid. Either is fine. All right, and that will finish us up here. Now, I want you to compare that with the reaction involving carbon dioxide. In all of the Grignard reactions we've looked at so far, the electrophile came before the arrow and the nucleophile was over the arrow. With carbon dioxide, a lot of times those two positions are switched, but these are still the two reagents involved in the first step. So I want you to take this general reaction pattern and predict the product of this sample one that I put over here for you. So pause the video, draw the structure, and then come on back. All right, welcome back. The carbon that used to be attached to the magnesium is now attached to the carbonyl carbon, the sp2 carbon of the carboxylic acid. So let's see how that happens. When you have carbon dioxide, it's a linear molecule, so you can draw it like this, or you can draw it left to right. But I want you to notice the hybridization of this carbon, because it's not sp2, it's sp, because there are only 2 electron clouds around that carbon. So nucleophilic attack. Pi electrons from one of these 2 double bonds has to go onto the attached oxygen, and I just chose that one. You could do the other one if you wanted to. And then again, we're to something that will just sit there until it finds a proton source. Now, at this one, I decided to show the aqueous acid as acid and water, just to show you what the options were. But either is fine. So since there was only 1 electron movement in step 1 and only 1 electron movement in step 2, I just did them together in sequence like this. But this is, if you want to label them, this is step 1, the nucleophilic attack, and this is step 2. So Grignard reagents will react with quite a few different kinds of compounds, both carboxylic acid derivatives and aldehydes and ketones, and carbon dioxide. There are a couple of other carbon nucleophiles that turn out to be important. One of them is the acetylide ion, which is just the conjugate base of a terminal alkyne. So if you go back and look in your notes on the alkynes chapter, you'll see what kind of a base it takes to remove that hydrogen. So I want you to take this general reaction pattern and draw the product for this. So do that and come on back. Okay, welcome back. So this part stays the same, and this carbon that it's attached to is still there, and this is the one that gets the other piece attached. Okay, so there's this, and the fourth thing is a hydrogen. You can either draw that in or not. And I tend to do things with triple bonds like that just because it's easier for me to tell where the sp hybridized carbons are. Now you'll notice that this is a polyfunctional molecule. I could do something and transform this OH group. You know, a lot of reactions there. We know some reactions about transforming a triple bond. So certainly there are more possible ways you can go with one of these compounds than with one that just ends up with one functional group. Same thing is true about the reaction of an aldehyde or ketone with the cyanide ion. You'll see this is a salt with the sodium cation, cyanide anion. The carbon is the nucleophilic atom. You can tell because you form the new bond between the carbonyl carbon and the carbon of the cyanide ion. All right, so take this general reaction pattern and draw me the product for this one. Okay, welcome back. So same kind of idea. And I'm going to feature this carbon just to remind myself of where it came from. The carbonyl oxygen is now in the hydroxyl group. The methyl group is still there. And then here's my cyano group. This is a polyfunctional molecule also. You know how to hydrolyze these guys and reduce them. You know how to take OH groups and turn them into a variety of things. All right, so please answer the question at the end of this video and then come on back.